simple harmonic motion, or as it's often referred to, SHM. This is a special type of motion where a particle moves in a straight line. The acceleration is always directed towards the centre, or mean point, of the oscillation. We've met this type of thing in some of our earlier examples. So we can see here that we have the particle over here to the right of the mean position, and therefore x is positive. The acceleration is back the other way. The centre point of the oscillation, the mean point, is O, as shown in the diagram. If the particle is at the position shown, x is positive, the acceleration is towards O, and therefore, in this case, negative. So the particle will slow down, and it's going to stop when it gets to B. It will then speed up, because remember the acceleration is still to the left, as it heads back towards O, achieving its maximum speed at O while it's moving to the left. And then we get the diagram below, which is the next time we're going to look at it. And we can see that the x is now to the left of O, so it's negative, but the acceleration is positive. So once we're to the left of O, it will accelerate to the right, therefore slowing down and coming to a stop at A. I've got B there. I've already changed this a few times. I'm going to change it in my notes. But if it's going this way and slowing down, it's going to be A where it stops, not B. Okay, continuing. Since the acceleration is towards O, the particle speeds up all the way to O, where it has its maximum speed, this time to the right. So, if you like, maximum velocity is always at O. This is an oscillatory motion, and the amplitude of the motion is A. And when I say it's A, we're saying that the distance from here to here is called A. This is the distance AO, or if you like, OB. Since the acceleration is always in the opposite direction to the displacement and is directly proportional to the displacement, we can express the acceleration as x double dot, which is the acceleration, is negative k squared x. So you might think of that as being A is negative k squared x, but we write this as x double dot, which is a way of writing d2x dt squared, which we know is acceleration. So, just in case you haven't met that before, the k squared ensures that the constant is positive, so negative k squared ensures that the acceleration is always in the opposite direction to the displacement from the mean point. We can go ahead and solve this differential equation. And we've used this before, v dv dx, negative k squared x. We've solved ones like this before. And so it's a separate and integrate. And doing that gives us the integral of v dv is the integral of negative k squared x dx. So v squared over 2 is negative k squared x squared over 2 plus a constant, and multiplying through by 2, and giving c as a new constant, v squared is c take away k squared x squared. Now, as discussed, we know that the particle comes to rest at the endpoints. Hence, v is equal to 0 when x is equal to a. So it follows that c is equal to k squared a squared. Therefore, v squared is equal to k squared a squared minus k squared x squared, or v squared is equal to k squared a squared minus x squared. Now, this one here is important, and we'll come across it again very shortly. So, in fact, straight away, looking at this, which is how it is written in the formula sheet. And we've got the formula sheet down here. Okay, and there it is, just there. It's handy to have that on the formula sheet because you don't need to remember all of these. See below, this can be rewritten as v is equal to k root a squared minus x squared. And we can solve this to find x because we know that v is dx dt. So that is equal to k root a squared minus x squared. Again, separate and integrate. So we get the integral of 1 over root a squared minus x squared dx is equal to the integral of k dt. So the inverse sine of x over a is equal to kt plus a. That gives us x over a is sine kt plus alpha. Sorry, I said a before, it's alpha. X is equal to a sine kt plus alpha, which is also on the formula sheet as shown below. Let's go and have a look at that one. And here it is just here. If the particle starts at the mean point, x equals 0 when t equals 0. That leads to alpha equals 0. So in that particular case, we can just use x is equal to a sine kt. If the particle starts at the right-hand endpoint, x is equal to a when t is equal to 0, and that leads to alpha being pi by 2. And since sine of x plus pi by 2 is cos x, we normally express this as x equals a cos kt. I think I might need just to explain that a little bit more. We know that x is equal to a when t is equal to 0, so we would have a is equal to a sine, if t is 0, 0 plus alpha, and we know that sine of pi by 2 is equal to 1, and that's how we get the alpha is pi by 2. So moving on, if the motion started at the left-hand end, we'd say x is negative a cos kt. Motions that start at points other than the centre or at the endpoints can be expressed as x equals a sine kt plus alpha or x equals a cos kt plus beta. Again, that one is on the formula sheet. Alpha and beta are angles in radians. Very important, we're working in radians here. Whenever you're using angles as numbers, you have to be working in radians. Plus we're doing calculus to be determined for the given situation. Since the start of the motion is t equals 0, the next time the particle is at the same point and headed in the same direction is when kt is equal to 2 pi. That should be readily apparent because when that is 2 pi, we've done a complete cycle. Remember, both sine and cosine have a period of 2 pi. So the period of the motion is t equals 2 pi over k. That is worth remembering as well, but it is on the formula sheet. I've never actually seen the frequency used, but it's there on the formula sheet. And all of this is shown on the formula sheet below. It's very handy. And this bit here, which we expressed before as x double dot is equal to negative k squared x, that defines SHM. So if you're given a situation and asked to show that it's SHM, showing what we've got there in that box will do the trick.